Lesson 5 in our look at consequences of the derivative. Lesson 5 deals with concavity, a topic that is familiar to us from our work last year, concavity, and the idea of inflection points. But I want to go way more than we did last year. Last year we said, okay, second derivative equals 0, and that worked for all the stuff we did with polynomials, but concavity is a little bit more deep than that, and that's where I want to go. I want to talk about concavity. That's the idea. So by definition, the graph of a differentiable function. Differentiable means that it's smooth. You can draw a tangent line at every point. The graph of a differentiable function, y equals f of x, is concave up on an open interval I for interval, if y prime is increasing on I. Similarly, f of x is concave down on an open interval I if y prime is decreasing on I. We're concave up if y prime is increasing. We're concave down if y prime is decreasing. As a follow-up, what do I know? If a function is increasing, its derivative is positive. So if y prime is increasing, y double prime is positive. And if y prime is decreasing, y double prime is negative. That drives home the definitions that you play with in a pre-calculus class that sort of plays a little bit with calculus. We just say, for convenience sake, second derivative is positive, second derivative is negative. But in reality, you're concave up if your derivative is increasing. I'll show you what I mean. So you've got some function, and it looks like so. This is some function y equals f of x. All through this area, right to about there, and all through maybe this area, right through here. The function f of x is concave up. Well, why do I say that? Because the derivatives are large negative, then smaller negative, then 0, then small positive, then large positive. The derivative values are increasing. And since the derivative values are increasing, the function itself is concave up. Similarly, large negative, small negative, 0, small positive, medium positive, large positive. Those slopes are all increasing from left to right. And so since y prime is increasing, y is concave up. By contrast, through this area in the middle, we have a concave down portion because we start with a large positive and then we go small positive and 0 and small negative and large negative. Those derivatives get smaller from left to right. Does that make sense? I hope so. That's what we mean when we talk about concavity. So I don't just want us to think second derivative is positive, second derivative is negative. I want us to think in terms of the first derivative. In the red parts where f of x is concave up, f prime is increasing. And in the blue area, where f is concave down, f prime is decreasing. So, determine the concavity of g of x equals x cubed minus 5x squared plus 3x minus 4. If I want to determine the concavity of that function, then I've got to look at g double prime. But I can't look at g double prime until I look at g prime. G prime is 3x squared minus 10x plus 3. G double prime is 6x minus 10. So what do I know? I know if I take a look at a number line, which is a line with numbers on it, that changes, g double prime changes sign at 10/6, or if you like, 5/3. G double prime is negative before and positive after. And so what do we conclude? We say that g is concave down on negative infinity to 5/3 because g double prime is negative. We can make a reference to g double prime. We can do that. We're allowed to do that. Similarly, g is concave up on 5/3 to infinity because g double prime is positive. We are allowed to say that. I want to drive home, though, that I could have used this guy. I could have used g prime. I could have said, here's g prime. G prime is some ridiculous graph, looks like this. Ballpark. No, it never goes negative. Whatever. G prime bottoms out at x equals 5/3. G prime is decreasing to the left of 5/3, and G prime is increasing to the right of 5/3. So the concavity argument still works. So what does that make 5/3? Well, that makes 5/3 a point where the concavity changes. And a point where concavity changes is an inflection point. A point of inflection. A point of inflection is a point where the graph has a tangent line and concavity changes. You have to be able to draw a tangent line at a point of inflection, and concavity has to change. The side note here, y double prime must change sign at an inflection point. It is not enough to just say, okay, I'm going to look for everywhere y double prime is 0. It's not enough for y double prime to equal 0. Y double prime has to change sign at an inflection point. Has to change sign. Okay, so find all inflection points for y equals e to the negative x squared. All inflection points for y equals e to the negative x squared. Well, inflection points come from the second derivative. So I'm looking at y prime, that's e to the negative x squared times the derivative of negative x squared. And then I'm looking at a second derivative. The product rule, it's so much fun. It's 1 prime 2 plus 2 prime 1. Wait a minute, prime 1 requires us to play the game again. And so y double prime is 4x squared minus 2 times e to the negative x squared. So I think to myself, e to the negative x squared is always positive. E to anything is always positive. So the e to the negative x squared gives me no inflection points. E to the negative x squared is always positive. But 4x squared minus 2, oh, that's a horse of a different color. That hits the axis twice at negative radical a half and positive radical a half. Furthermore, 4x squared minus 2 is a happy parabola. It goes plus minus plus. Zeros here. And so I ask myself, where are the inflection points? The inflection points are the places where the second derivative changes sign. And the second derivative is going to change sign at negative radical a half and positive radical a half. So I've got inflection points at negative radical a half something and positive radical a half something, because y double prime changes sign at x equals plus or minus radical a half. So what are those values? What are the y values at those places? Well, we substitute the x values into the original equation, and we get e to the negative 1/2 and e to the negative 1/2. So when I'm looking for inflection points, I am looking for places where the second derivative changes sign. Got it? Okay, one more. I want to pull it into a theoretical context. I want to consider the graph of f prime of x, where f prime of x is this thing that I am about to create. Well, I already created it, but I'm going to draw it. And the graph looks something like this. It's got a nice big lumpy thing there, and then that kind of ooh, and that holy mackerel. And if you don't draw it exactly that way in your notes, you can't pass. That's the way it goes. And I want to see if we can put some stuff together. I want to know on what interval or intervals is f of x increasing, f of x concave up. I want to know, where does f of x have a max, a min, an inflection point? These would be local maxes and mins. And so if you're one of those people that wants to try it on your own, hit the pause button, give it a go, see if you can find out where f of x has increasing, where f of x is increasing, where it's concave up, where it's got a max and a min and an inflection point, bearing in mind that the graph you see is the graph of f prime. It's not the graph of f. So hit the pause button, and then we'll see how we did. You didn't really hit the pause button, did you? Okay, maybe you did. So where is f of x increasing? Well, f of x is increasing where f prime is positive. And f prime is positive between -2 and 0. F prime is positive between -2 and 0. And so I say that f of x is increasing on -2 to 0 because f prime is positive. And then I'm supposed to ask, where is f of x concave up? Well, f of x is concave up where f prime is increasing. And f prime is increasing from -2 to -1. and then again from what appears to be 1 to 2. I know somebody's going to get into a measurement war with me. And then again from what appears to be 3 to 4. So whatever you thought those minimum points were to whatever you thought those maximum points were, -2 to -1, 1 to 2, 3 to 4. Where does F have a local max? F has a local max where F prime switches from positive to negative. So where does F prime switch from positive to negative? That happens at x equals 0. I don't know what the y value is because I don't have an F function handy, but I know wherever x equals 0, that's where the max is. Where does F have a min? F has a min where F prime switches from negative to positive. Well, that never happens. There's never a min. There's never a local min, unless you want to consider the right endpoint, and some people do, because they're going to say, oh, here's the story. F of x is increasing, 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 and then f of x is decreasing, 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 decreasing. And that's okay if you want to play the game that way. If you want to say that x equals 4 is a local min, the College Board's not going to give you a hard time. The way that question's going to be phrased is, where on the open interval -2 to 4 does f of x have a local min? And then inflection points happen where f prime switches from increasing to decreasing or vice versa. And that happens at -1, 1, 2, and 3. Those are the places where f prime changes from increasing to decreasing or decreasing to increasing. Okay, so when we come back together in class tomorrow, I've got some other similar questions. I want to drive the points home for you, but I hope it goes well for you in your practice time. Wonderful. Thanks, everybody.